Hello and welcome to my presentation. My name is Alex Thatcher and I am a reservoir engineer for Oilfield Production Consultants, OPC. The title of our paper is Analysis of Dynamic Reservoir Behaviour Reflected in Long-Term Surveillance Data, a workflow driven by pressure rate deconvolution combined with reservoir simulation. The subject of this paper is analysis of reservoir dynamic behaviour reflected in long-term surveillance pressure and rate data using generalized and enhanced pressure transient analysis (PTA) techniques. Often, dynamic analysis using PTA is associated with short-term well test type data, such as exploration and appraisal well tests, while production data analysis (PDA) techniques, e.g. material balance analysis, rate transient analysis, decline curves, etc., are used for long-term data on the scale of months and years. Yet PTA is more than capable of analyzing long-term data, and in the right conditions can give a much more detailed and richer analysis than PDA techniques. It is the long-term dynamic data that reflects large-scale reservoir properties far away from the wells, such as large-scale rock property heterogeneities, flow barriers, faults, pinch-outs, etc., the connectivity across the reservoir, large-scale characteristics of external reservoir boundaries, and the volume connected to producing wells. The objective of this analysis workflow is to recover and understand all these features in one integrated approach, covering all transient flow regimes extending to the scale of the entire reservoir. Finally, applying these techniques and gaining this reservoir knowledge early in field life offers an opportunity to de-risk and adjust field development plans to maximize project value. Our approach presented is built on PTA and is generalized to be able to handle long-term surveillance data from development wells covering field startup all the way to several years of production. At the heart of PTA and this analysis approach is the principle of superposition, which strictly speaking is applicable to only single-phase flow. In some fields, single-phase flow may last for the majority of field life. In those that develop multi-phase flow early, data acquired at field startup provides a crucial opportunity for analysis before complications occur. On the other hand, the methods in our approach are sufficiently general to analyze complicated reservoir and well systems, e.g. double porosity permeability reservoirs, horizontal wells, unconventional multi-frac wells, etc. On this slide, I discuss the enhancements made to PTA to allow for analysis of long-term surveillance data. The requirement that fluid properties do not depend on pressure is one of the necessary requirements for the conventional use of PTA. For oil reservoirs, this is generally the case, at least at the beginning of field production. But for gas reservoirs, especially those undergoing significant depletion, gas properties depend on pressure, and this makes the problem of fluid flow in the reservoir nonlinear and inconsistent with superposition. However, we apply pseudo-pressure and material balance pseudo-time transforms to linearize the flow problem and make it consistent with superposition. Conventional PTA typically analyzes individual flow periods, such as pressure buildups, in isolation. However, when analyzing surveillance data, there is a need to integrate the long-term well pressure behavior that evolves over time, as it is this long-term trend that reflects the reservoir parameters far away from the wells. This is achieved through the use of pressure rate deconvolution. Pressure rate deconvolution is a method for converting the pressure and rate data obtained from a well operating under variable rate conditions into a much simpler form of a constant rate drawdown pressure response function. The deconvolution approach is not based on the automatic pressure rate deconvolution technique, as this relies on mathematical algorithms and regression techniques which are not robust enough to be used with data sets acquired during long-term production operations. Instead, we use specialized software which manually adjusts the drawdown response function so that the results of convolution match observed pressure data. More on this later. Finally, reservoirs are typically developed with multiple wells, hence long-term surveillance analysis is fundamentally a multi-well analysis problem. The workflow described in this paper handles the multi-well environment through the use of multi-well deconvolution. However, for today's presentation, there is simply not enough time to discuss the multi-well environment. Now we demonstrate this workflow on an example dataset from a well in a gas reservoir. In blue is the historical downhole pressure data recorded by a gauge, and in green is the historical gas rate. We are dealing with 5 years worth of production data, and within this data set there is a number of pressure buildups over time. 4 of these are highlighted in red. The first step in our analysis workflow is to assess if the transient pressure behavior is consistent over time. We use conventional PTA by overlaying these pressure buildups from early to late life on a Bourdais derivative plot normalized by rate. This assessment shows consistent transient pressure behavior, which provides an initial indication of the linearity of the system, which is a key requirement for successful pressure rate deconvolution. However, we also see that the dP curves separate vertically, and this is an indication of changing skin factor. It is concluded that this is due to turbulence, a rate-dependent skin. Therefore, flowing pressures are nonlinear and inconsistent with superposition. They should be ignored during the pressure rate deconvolution analysis, and we should expect not to be able to match all of the flowing pressures. Here we complete a basic demonstration of the deconvolution method using the example dataset. On the left-hand side is where we will perform pressure rate deconvolution. The blue line is a reference PBU, and the red line is what we call the response function. On the right-hand side is the data plot. In green is the historical gas rate, and in blue is the pressure measurements from the downhole gauge. The red line is the pressure calculated from pressure rate deconvolution using the convolution equation. Now, with the response function drawn the way it is in infinite acting radial flow, there is a clear mismatch between the red line and the blue line. The objective here is to find a response function that sufficiently matches the historical pressure data, and this is done interactively by the engineer using this specialized software. So when I play the video, please keep your eyes moving between changing this response function and the match on the data plot. So let's play the video. Here we use the reference pressure buildup to help guide our initial shape of the response function. But on the data plot, we clearly need more pressure depletion. So in late time on the response function, I draw a unit slope. And this unit slope represents the connected pore volume to the well. I start by decreasing this connected pore volume by moving this line to the left. And watch how we can get a closer and closer match on our data plot. We have to be very precise when selecting position of unit slope. But it also looks like my reference PBU in blue has shifted, and this is due to the material balance pseudo-time transforms accounting for the long-term variation in fluid properties. We simply adjust our response function back over this reference PBU and make some final adjustments as shown. Now on the data plot, we have sufficiently matched 5 years worth of production data. Finally, we plot the average reservoir pressure connected to this well as shown by the green thick line. Now that the response function is reconstructed, the next step in the analysis workflow is to interpret and decouple well and reservoir parameters. So let's analyze this response function. First, we see the end of wellbore storage. Then we see a very brief radial flow period. From this, we can derive permeability thickness, permeability, and total skin. Next, we see a doubling of the derivative into hemiradial flow. This is indicative of a single fault near to the well. Here we can determine the distance to this fault. Then we transition into linear flow. The well is between two parallel faults. From this, we can determine the channel width and the distance to each fault. Finally, the response transitions into a unit slope, meaning we are in pseudo-steady state. We are now out of transient flow regimes and into the world of material balance. This tells us that the reservoir is closed. From this, we determine the time to pseudo-steady state, the pore volume and gas initially in place connected to the well. We also determined average reservoir pressure, as shown in the video example. Now, all of this is derived from pressure measured at the well location, but here we have transformed the pressure and rate data into an image of space. This is what distinguishes PTA from production data analysis, as it is a richer and more detailed analysis technique that considers all transient flow regimes all the way to the limits of the reservoir. This is not a clear picture. The true reservoir shape can only be characterized as long and narrow, which reaches the limits of the reservoir after 1.5 years. However, the pore volume connected to the well is very well defined. Much better and more detailed pictures of reservoirs are derived from seismic and geological data presented in the form of reservoir map. This is a reservoir map of our workflow example. There are actually 3 wells in this field, however the well we are analysing is shown as well 1. According to the map, there are several faults running along the reservoir structure. There is one major fault on the map that runs through much of the reservoir length that could potentially cut off a strip of the reservoir structure into a separate fault block. Now, the dynamic analysis of well 1 we just conducted did not identify any signs of pressure interference of well 1 with the other 2 wells in the structure. Hence, it is concluded that the above major fault does extend all the way to the south reservoir boundary, and the fault block is indeed like a long and narrow channel. So while the map shows a clearer image of a reservoir in terms of spatial arrangement, it is based on static data, and it does not clearly indicate how the reservoir is plumbed together. The way to achieve this integration is through the incorporation of reservoir simulation into the dynamic analysis workflow. To do this, a special 2D single-phase simulator was developed. This is not a finite difference or finite element type simulator like the majority used in the industry. It does not use aerial gridding when solving fluid flow problems in the reservoir. It is based on a numerical boundary element solution. Here I have a short video clip demonstration of the simulator in action. On the right-hand side, shown in blue, is the results from pressure rate deconvolution that I derived earlier. It is this plot we will match our simulation model to. On the left-hand side, I have quickly drawn this red polygon over the field map. This is our simulator. For demonstration purposes, I do not honor the reservoir map exactly, and I simulate the response. So let's play the video. We right-click, do simulation, and the results of the simulator are shown as the black markers on the right-hand side. Now we have the permeability correct and we have the distance to the near fault correct, but the timing of linear flow is too early. The map does indeed show a wider channel, so we adjust our simulator as shown and we simulate again. Now the timing of linear flow is correct, we see in very late time our unit slopes are not matched. We need to increase the volume of our simulation model to equal the volume as per our results from pressure rate deconvolution. In doing so, we end up drawing the simulator as shown and we simulate again. So now we have the unit slope in the correct position. However, we have a subtle mismatch in the response function from 150 hours to 2000 hours. This mismatch is caused by the fact we are using a homogeneous model with a single permeability. The map actually shows permeability heterogeneities, so we introduce these into our model as shown on the next slide. We split the polygon into several regions and distribute the permeability as per the geological understanding, as shown on the left-hand side. Now in red on the right-hand side is the results from pressure rate deconvolution. And when we simulate this model again, we see the results shown as these black dashes. Now we have a perfect match on the response function. Finally, we take the simulated response function, plug it into the convolution equation, and solve for well pressure with the well rate. The historical downhole pressure is in blue, and the reservoir simulation is in black. We see we have an excellent match on the sequence of pressure buildups, and this further confirms our understanding of dynamic data, which points to some large-scale permeability heterogeneities within the reservoir. Summary and conclusions. A methodology for dynamic analysis of long-term surveillance data has been developed. With the reliability of permanent downhole pressure gauges and well rate metering improving, we have a wealth of data that contains important reservoir information. This is an analysis methodology for interpreting such data sets. It is applicable to the data that reflect single-phase flow conditions in the reservoir and that are consistent with the superposition principle. The enhancements made to conventional PTA techniques were accounting for long-term variation of fluid properties and a robust pressure rate deconvolution technique that can be used in the single and multi-well environments on production data acquired during routine operations. As part of this workflow, a special 2D single-phase simulator was developed to quickly understand if the results of analysis were consistent with the geological understanding. The analysis approach and the entire workflow yield a much clearer picture and understanding of the reservoir compared to traditional production data analysis techniques. Ultimately, this will help to solve complex reservoir problems quickly and drive important future business decisions for the development of a field. Finally, I would just like to raise the point that this is not something theoretical or a proposal of how to perform the analysis. This technique has already been developed, implemented, and used in practical analysis on several significant projects worldwide by different people. It has been used on a wide variety of reservoir systems, well systems, the multi-well environment, and fields where the principle of superposition eventually breaks down after several years of production. Thank you for listening to our presentation today, and I hope you enjoyed it.